Hello everyone, my name is Jeremy McCullough and I'm speaking on behalf of Group 11. Today you'll hear from myself and a few of my teammates on why we believe that our design is the best solution to the problem. We've split our design into what we believe are the three major components. These components are mechanical hardware, electrical hardware, and control software. First, I'm going to tell you about our mechanical hardware. This is the overall mechanism by which our robot will physically shoot each ball into its proper cup. Our design uses a gravity-based launcher. We decided that a gravity-based launcher would be the easiest because it didn't involve any complex pressure regulation systems, didn't involve a whole lot of complex mechanical parts, and gravity is fairly predictable. For our launching mechanism, the ball is held at the end of the tube by a stopper mechanism. When the tube is properly aimed towards the particular cup that the robot's trying to shoot in, then the stopper mechanism will let go, allowing the ball to fall out of the tube, bounce off the platform, and into the cup. The arm's rotation will be handled by a DC motor placed at the back of the arm. Attached to the motor will be a wheel which runs along a circular track. When the motor runs forwards or backwards, it will change the angle of the tube and allow it to aim for a particular cup. The ball's trajectory is also dependent upon its horizontal and vertical velocity. In order to account for this, we've allowed the tube to be tilted and moved back and forth, as in closer and further away from the bounce platform. The tube will be suspended from a moving platform which is attached to the rotating arm. This platform will be used to move the tube closer and further away from the bounce platform. This is accomplished by the use of a lead screw mechanism. Lead screw mechanisms are an efficient way to move things back and forth and are often used in CNC machines because they allow for a fair amount of torque to be applied with a lot of accuracy as well. The launcher tube itself can be tilted by use of a servo. Servos are cheap, powerful, and accurate, which is why they're often used in robotics. When all of these degrees of freedom are combined, the robot will be able to easily aim for any cup on the game platform. Each motor will utilize feedback so that the robot knows exactly where it's pointed at a given time. Whenever the robot is aiming for a particular cup, it will look in a database of known position values. It will use these position values as set points for each motor so that the results are highly repeatable. Overall, we feel that our mechanical design is cheap, efficient, accurate, and doesn't involve a lot of moving parts. We came up with several design concepts initially, and we believe that this is the best one. Next, I'd like to hand you over to Stephen Thompson, who will discuss the electrical portion of our hardware design.
The next few slides will explain the electronics of our prototype design. First, the stepper motor will be used to move the ball tube toward and away from the window. It is a bipolar, two-phase motor and has 4 wires. The first pair of wires, the red and green ones, makes up the first coil, while the other pair of yellow and blue wires makes up the second, as shown on the datasheet. The motor will be driven by an H-bridge. The H-bridge will take 4 inputs from the Q4 board, which will control the stepper motor coils through the 4 wires to determine the direction of rotation. The DC motor will determine the theta position of the tube by rotating it along a curved track. This motor will be driven by a Darlington driver, accompanied by some additional circuitry, as shown. The design is for safety precautions so that both inputs don't destroy the bridge when both inputs are active. A potentiometer will be used to use the current DC position as feedback to make necessary corrections. The prototype will use 2 servos, one to tilt the tube up and down, and the other to hold and release the ball. They will be driven by a 5-volt supply and controlled by analog input. Lastly, a 5-volt linear regulator will be required to step the voltage down from 12 volts to 5 volts to provide proper supply to the devices that require VCC at logic level. We will be using the LM7805 for this prototype.
So on the software end of this, we have the software module, which ultimately is going to be controlling the hardware. It begins with the image analyzer. This is a tic-tac-toe algorithm to process those images, and then it has the MATLAB Q4 solution to perform the closed-loop control so that we can actually move the hardware. The image analyzer is going to take an image, obviously, from the provided camera. MATLAB is then going to be used to process this image using such things as filtering for a certain color, maybe say for the green light or a certain color ball. It'll be used to find the cups and actually locate what's collected inside the cups. The board will then be digitally inscribed. Say if you have two balls on top of each other, the processing should take out and determine which ball is actually on top, and it'll record this data in X's and O's in some form of data and provide that to the tic-tac-toe algorithm. The tic-tac-toe algorithm is almost going to be like an AI, except for it most likely is going to contain a bunch of basically conditions to say where to shoot the ball. Say, for example, if you had two X's on each side and we needed to block the opponent from winning the game, then that would obviously be the highest priority move, and as soon as the game recognized that was the situation, we would pick that cup to shoot to. Ultimately, if the board is open, we'll probably give the tic-tac-toe algorithm a predefined spot to shoot it to. In other cases, could be handled situationally. This hasn't been fully worked out. We've done a lot of research on it, but ultimately, we know that if nothing else, it'd be kind of complicated. We could at least take the board and brute force program exactly where to shoot the ball in every single scenario possible. Obviously, we're not trying to do that, but we know that that's at least an option if it needs to be at the end of the day. Once we pick which cup to shoot to, we're going to use the MATLAB Q4 solution, which is made up of MATLAB and then the Q4 card. We're going to use this to take the data in and send a signal back out to these motors to control where they're going to. It's obviously using the potentiometer system that we used before. The information is going to come in from the tic-tac-toe algorithm in the form of, or we haven't actually gotten this far, but we're basically going to put in an angle and then expect the desired angle to be output using the closed-loop control.